I hope I confused you enough. And after this, I'm very happy actually to introduce questions, comments, remarks. Good. To introduce Maria and Gidea, whom we adore. And I didn't know how to top love and from Yeshiva University. Oh, we really like you, Dwayne. And his talk is on about global effect of non-conservative perturbations of homoclinic orbits to a normally hyperbolic invariant manifold. And thank you very much for accepting our invitation.
Well, thank you very much to the organizers, whom I adore. It's a pleasure to be here. So this is a joint work. I mean, it's based on two separate joint works. So Samuel Akingbade, it's a current PhD student. Maxwell Mather, it's a former graduate student. And the work is based on two papers. One is Akingbade and Teresara, and the other one is Mather and Rafael de Ayave. So basically, we use the Hamiltonian formalism, autonomous Hamiltonians, to describe, for instance, the motion of physical systems that conserve total energy, for instance, the motion of planets, asteroids, satellites, etc. But these are ideal models, because in real life there are always some dissipative forces. For instance, satellites are subject to atmospheric drag. So when you have dissipation, typically you lose energy. But what I want to show today is that if you combine the effect of time periodic Hamiltonian perturbation plus dissipative perturbation, if you combine them together, it is possible under certain conditions to actually gain energy. And I will discuss a very simple model, so it will be very concrete and very specific problem on which I will try to illustrate this idea. So the model consists of a rotator, so a purely elliptic system, plus a pendulum, and the pendulum contributes with hyperbolicity, so you have a hyperbolic fixed point whose stable and unstable manifolds coincide. And to this system, we add two perturbations. One is a time periodic Hamiltonian. So we have this extra variable, which is time. It's a time-dependent perturbation. And epsilon, it's the smallness parameter. And a second parameter, it's a dissipation. So this is a vector field, so it's not a Hamiltonian. So this will be added to the equations of motion. There is also an epsilon parameter in front of this, so we want this to be small. And there is a dissipation, another dissipation parameter that acts on the momenta, on P, and on the action variable of the rotator. And this dissipation coefficient, we choose to depend on epsilon. So overall, the effect of the dissipation is encoded by this quantity, which is epsilon rho of epsilon, rho being a function. And you see here, there is another parameter that it's part of the effect on the action coordinate of the rotator. So this omega star parameter, I'll refer to this a little later, and essentially it's added for fun. I hope that we are going to have fun, actually. So these are the equations of motion. So you see, this is, let's just say, the integrable part of the Hamiltonian. It's integrable with singularities. And this is the small perturbation, which has two parts. One is the Hamiltonian perturbation, and the other one is the dissipation. And sometimes I will formulate some results in a more general form. So I'm going to combine this together as a single vector field, which I'm going to call x1. So here x1, it's the Hamiltonian vector field from the perturbation, from the time-dependent perturbation, plus the dissipation part. So again, the objective is to show that there exist trajectories for which the energy of the rotator, or if you wish, the action of the rotator, grows by some quantity which is independent of the size of the perturbation, like order 1 growth over time. So this is the main result. So assume that the Hamiltonian perturbation and the dissipation coefficient satisfy certain conditions, and these conditions will appear later on. Then there exist two values, I1 and I2, of the action of the rotator. So these two depend on H1 and then epsilon sufficiently small such that every time we choose a Diophantine number omega star between I1 and I2, for all epsilon sufficiently small, there are orbits that start below I1 and end up above I2. So they travel a distance of order 1. So,
sorry, I don't understand. What is the role of omega star in this thing?
Yes, so you see, this assumption is unnecessary. So let me justify it a little bit later. So this is an extra parameter that I say it's for fun, and we can give up this parameter altogether if we wish. So, but I think in the next slides it's going to reveal itself. So the point is that if you have only the dynamics of the rotator, so take the dynamics of the rotator and add only the dissipation to this, and if you start below this, okay. So this omega star, it's in this example, it's creating an attractor. And the attractor is like an invariant torus. And the idea is that if you only use the dynamics of the rotator, if you are below the attractor, you cannot cross it. So, but if you involve both the Hamiltonian perturbation and the dissipation, you are going to have some orbits that are able to jump over this attractor and move order 1. So this is, let's say in a nutshell, what is the role of this omega star. Okay?
So you want to show that in, yeah, but I mean the full system is, what is it, in 4 dimensions. So
it's
the attractor is not, it cannot stop.
Yes, yes, that is correct. Yes. So I'm just saying if you use only the inner dynamics, it stops, but you have to use the inner and the outer dynamics in a combination too. Yes. So this is related to the Arnold diffusion problem. So this goes back to an example that Arnold proposed in 1964, and Arnold's original example, it's a rotator pendulum system, and he added a time periodic Hamiltonian perturbation of a very special type, and he conjectured, I mean, he proved that there exist diffusing orbits. These are orbits for which the energy of the rotator grows by an amount independent of the size of the perturbation. This is for all sufficiently small value of the perturbation parameter. So the gain of energy is independent of the smallness parameter. So he conjectured that this is valid for a generic system, and this is the formulation of Arnold. So he said this, he refers to this transition chain mechanism that I'm going to briefly review later, and said this is a universal mechanism of instability. It is applicable to the general case, and also said is applicable to the problem of 3 bodies. And somewhere in the book by Chirikov, there is also mentioned that maybe this is possible to apply to systems with small dissipation. So I'm going to focus on this part when you add small dissipation, and essentially you want to prove Arnold diffusion. So now I'm going to quickly recall the geometric mechanism of Arnold, so the transition chain. So the idea is the phase space of the rotator forms a so-called normally hyperbolic invariant manifold. So this is a manifold which has stable and unstable directions, and the contraction and expansion in these directions are stronger than the dynamics on the manifold itself. So then you can distinguish two dynamics. One is the outer dynamics along the homoclinic orbits to the NIM. So NIM is short for normally hyperbolic invariant manifold. And you have the inner dynamics, the one restricted to the NIM. So, the idea is that Arnold constructed transition chains, so essentially invariant tori connected by heteroclinic orbits between nearby tori. So he constructed a so-called transition chain of tori. And people after Arnold, also people in this audience, developed other mechanisms of diffusion. And they are mechanisms that besides KM tori, they involve secondary tori, Aubry mother sets, and other type of objects. So this is what Arnold referred to transition chains of tori, and now these transition chains can involve some other objects. So I want to, okay. So for Arnold, the idea is that you have to have invariant tori or other nice objects in the NIM, and you have to have transverse intersections of the stable and unstable manifolds in order to construct this tori. So what happens when you add a dissipation? So this is, in general, so this is a little cartoon. So it's not exactly what happens in our example, but I want to sort of illustrate what are the worst case scenarios. So this is like first course in ordinary differential equations. So you have the pendulum, stable and unstable manifolds intersect. When you add dissipation, then you lose the intersection of the stable and unstable manifolds. So this is something that you need it in the transition chain, and there is a risk that it may go away. So you have to take care of that. The other thing is that the inner dynamics, many of the beautiful objects that you can use in the Hamiltonian case, like KM tori, secondary tori, when you add a dissipation, they may disappear. So there are some KM versions for systems with dissipations, and I'm using a version for conformally symplectic systems. And the idea is that under the right assumptions, you end up with only one invariant circle surviving the perturbation, and this is an attractor for the system. So this is the type of barrier that it's a barrier, as Carlangelo said, it's only for the inner dynamics, but this is the only reason that I put this assumption on the omega star, in order to have a barrier. But the proof works without this assumption at all. So we don't need this assumption. So as I said, it's more or less for fun. So the frequency has, in order to have a KM torus surviving the dissipative perturbation, then you need the frequency, of course, to be suitably chosen, because otherwise you can create objects that are more complicated. So this is a picture of the standard map plus a perturbation that doesn't take this frequency to be Diophantine. So you have more complicated objects like Birkhoff attractors, but you see that there are other attractors spread out in the picture, so they sort of create all sorts of problems in the phase space.
So this is the dissipative standard map?
Yes, this is the and in the first case, this is in the sorry, I'm going back. So this is with adjusted parameter, with adjusted frequency, and this is with non-adjusted frequency, which doesn't give us the Km. Okay, good. So now is going to be a very quick review of some of the basic objects that we are going to use towards the main result. So a quick review of normally hyperbolic invariant manifolds, as I said. So you have a manifold that it's for inside another manifold. So this is the general case. So the tangent bundle of the big manifold is split into a tangent bundle to this NIM plus an unstable bundle and a stable bundle. And the expansion and contraction rates in the tangent to lambda are dominated by the expansion and contraction rate in the stable and unstable bundle. So you have like a spectral gap condition. And so this is roughly the essence of the definition. And as a consequence, you have stable and unstable manifolds of lambda. Their regularity depends on hyperbolic rates. These stable and unstable manifolds of lambda are foliated by stable and unstable leaves. These are one-dimensional objects. And associated to these leaves, you have a canonical projection. So for the stable manifold, you have a point on the stable manifold of lambda, and there is a stable leaf, and you follow the stable leaf to the base, to the NIM, and that is one of the projections, omega plus. You do the same thing for the unstable manifold. You follow the unstable leaf until you reach lambda, and this is the other canonical projection. If the stable and unstable manifolds of lambda intersect transversally, and we need a stronger transversality condition that I'm not going to describe, then these projections are local diffeomorphism. You can further restrict this homoclinic manifold in order to have these diffeomorphisms rather than local ones. And if that is the case, you can do a composition between the omega plus and omega minus inverse. So, and this is the scattering map. So this is the main tool that we are going to use to prove diffusion. So let me explain it geometrically in two ways. So you have a homoclinic manifold. Choose a point on the homoclinic manifold, and there is a unique stable fiber through this point, and there is a unique unstable fiber through the same point. And the scattering map takes the foot point of the unstable fiber into the foot point of the stable fiber. You have to put the proper restrictions in order for this to be well defined, and diffeomorphism is not defined everywhere on lambda, it's only locally defined, but this is all you need. Yes, please.
In what curves are they projected? Sorry?
Say again?
What represent the curves?
The curves, okay. So these are the fibers, so these are geometric objects, but if you actually follow the homoclinic point, so the homoclinic point, the fibers are not invariant, are equivariant. So if I apply the map to one of these leaves, the leaf will move with the map. So the base point will move with the map. So the idea is that if you take a homoclinic point and you start to iterate it, of course, let's say on the stable manifold, it will approach the forward image of the point in the base. And if you take the inverse, iterate of the homoclinic point, it will approach asymptotically a point, the forward image of the base point. So the scattering map is a geometrically defined map, but the homoclinic map, it doesn't really follow the red and blue, but it follows the dotted line. So that's a segment of the homoclinic versus the scattering map. Did I answer your question? Sure. And this is what I'm saying here in these two lines, that the forward image of Z approaches the forward image of Z plus, which is the stable foot point. So it has been proved in Dershanzerab and Sarah that if you are in the symplectic world, this scattering map is symplectic. But this is not going to work for us because when you add the dissipation, presumably you destroy the symplecticity. I have to do 2 more slides about sort of reviewing these tools that work in the Hamiltonian case. So, so suppose that I have so this is, if you wish, the pendulum rotator system, and I only add the Hamiltonian perturbation, no dissipation yet. And this is a time-dependent Hamiltonian, so let's just say that we take a Poincaré section and you reduce it from a flow to a map. There exists a normally hyperbolic invariant manifold for the unperturbed system. This survives the perturbation. Then you have normally hyperbolic invariant manifold for the discrete system associated for the Poincaré map. So everything reduces now from flows to maps. And of course, the scattering map is also reduced from the flow case to the map case. And the main idea is that you can expand the scattering map in powers of epsilon. And the first order, I mean, this is always true, but what is not true is that the first order term, it's a Hamiltonian vector field. So if the perturbation is Hamiltonian, then the scattering map, when expanded, the first term or first order of the perturbation, it's a Hamiltonian vector field for some explicit function L star, which I'm going to maybe refer to this later. But what I want to say for now is that this is a Hamiltonian vector field. Again, this is not going to work for us in principle in the case when we have dissipation added to the system. This is one of the qualitative results that we proved with dell'Insubria and Serrat. So if you have this type of expansion of the scattering map, if you look at it, you can say that the scattering map is the Euler map associated to this vector field. So this is like the Euler procedure to approximate solution of ordinary differential equations, essentially. So that means, and by the way, another thing that I wanted to say is that this function L star is independent of the perturbation. So there is no epsilon dependence here. So this is like order 1 quantity. So now you have a solution. So this is in the NIM, in the normally hyperbolic invariant manifold. So you have a solution curve to this Hamiltonian in the NIM. And the scattering map is just the Euler map associated to this solution curve. So you can iterate the scattering map. And the iterates of the scattering map are going to follow the curve. They are going to stay close, at least for a while. So you have some sort of pseudo-orbit that mimics this curve. And this curve goes order 1 because the function L star is defined on an order 1 domain. So if your inner map, if the dynamics restricted to the NIM satisfies Poincaré recurrence, which is automatically satisfied in the symplectic case, provided that you stay within a domain of finite measure, then it turns out that this pseudo-orbit of the scattering map can be shadowed by a true orbit of the system. Again, what is going to happen in our case is that if you put the dissipation, you lose the Poincaré recurrence in the normally hyperbolic invariant manifold for the inner dynamics. Okay? So I'm sort of explaining what we have done in the past and what are the obstacles to apply these methods for the case when we have dissipation. All right, so now I'm going to consider the case when you have this non-conservative perturbation, which I remind you, X1 stands for a general non-conservative perturbation. In our case, it's a Hamiltonian perturbation plus a dissipation. And these are a little bit of technical ballet. So you have a normally hyperbolic invariant manifold for the unperturbed system. You work in the extended space, so you want to make the time as an as a dependent variable. So you in the extended phase space, you have a normally hyperbolic invariant manifold for the extended flow. And then it's easy to compute the scattering map for the unperturbed system, which is the identity. And you have persistence of normally hyperbolic invariant manifold, provided that the perturbation satisfies some regularity conditions that are uniform. So the first thing that we want to do is that now we have a non-conservative perturbation. We want to establish condition that the stable and unstable manifolds of the NIM intersect. So under which condition you have the intersection of these manifolds. So we can describe the stable and unstable manifolds in some convenient system of coordinates that is symplectic. So I'm just showing here like a two-dimensional picture, but what is actually happening, it's a five-dimensional picture that we cannot visualize. So for instance, we can use as one coordinate the energy of the pendulum, and the other coordinates is the time to travel along a level set of the energy. So one coordinate, the vertical coordinate is energy of the pendulum, and the other coordinate is time. And you can describe the stable and unstable manifolds as graphs over these coordinates. And in the case then you don't have any perturbation, these manifolds correspond to the zero level set of the energy of the rotator. So now there is a little bit of Melnikov theory. So if you want to compute, so now this is done for a general perturbation. The perturbation, I'm not making any assumption on this perturbation except that it satisfies some regularity condition. So you can compute the stable, the distance between the stable and unstable manifold at a current point. And you can express this as a Melnikov integral. So this is a directional derivative. You take the vector field, which is the perturbation, as a derivative, and you take the derivative of the energy of the pendulum, and you estimate it along a homoclinic orbit of the unperturbed system. You subtract from this the same derivative along a matching orbit in the inner system, in the normally hyperbolic invariant manifold, and you get this integral, which is an improper integral, and it's a convergent integral, and it's actually it's quickly converging. So this is good for application. So this is up to order epsilon squared, the distance between the stable and unstable manifolds. So if you want them to intersect, you want to have that there is a non-degenerate zero of this function. So now I'm going to our particular perturbation, which is Hamiltonian plus dissipation. So we can compute this explicitly, and we can split the Hamiltonian part and the dissipation part. And this epsilon rho, epsilon is the dissipation coefficient, appears as a separate integral. And this is the same Melnikov function that I will get. The first integral is the same as if I have no dissipation at all, and the dissipation appears as a separate term. So if there is a non-degenerate zero, so I take, let me do here maybe. So I forget about the epsilon. So if I take only these two integrals without the epsilon. Epsilon disappears. So if there is a non-degenerate zero of this quantity, then we know that for all sufficiently small epsilon, we have transverse intersection of the stable and unstable manifolds. Okay? So this is an if-then type of condition.
I don't understand. Rho epsilon goes to 0. What is rho epsilon? I got confused.
So rho epsilon, so let's see, I'm going to go at the beginning. It's
The size of the dissipation.
yes, so the size of the dissipation has two parts. So it has this epsilon that goes in front, and it has a rho epsilon, which is a function. So for the time being, I'm not saying much about rho epsilon, and I'm going to put conditions.
I don't understand, because the Hamiltonian part will give you an intersection of order 1. So how do you know that the other one doesn't spoil?
Yes.
You have some condition of rho epsilon for that.
Yes. So this will come after this. You can give my talk because you sort of anticipated. Okay, so no, it's a pleasure. It's a pleasure to. It's like in chess. You guess the next move, you win. So I think I'm here. So this is Carlangelo's slide. So if rho epsilon goes to 0 with epsilon, then you have a genericity type of result. So if rho is sufficiently small compared to epsilon, of course, once you have a transverse intersection without the dissipation part, rho epsilon is going to be sufficiently small, so you move this only a little bit, and then you have transversality again. So you have this is an easy genericity result, provided that rho epsilon goes to 0 as epsilon goes to 0.
Sorry.
Yes.
At which rate rho goes to 0?
So at this point, it can be any rate, because all you need is that you have compare a order 1 quantity with a quantity that depends on epsilon. So if so this is like order 1. So all you need is this is small. Yes. So if epsilon is small, that is small. So this will be killed by the other one for epsilon sufficiently small. All right.
But then these affect the time of diffusion?
Yes, definitely. So, so if you want to get into estimates of the time of diffusion, of course, that you have to be very specific. How do you choose rho epsilon in order for the mechanism to work and gives you a specific time? So, very good question. Yes. So I'm sort of giving more and more conditions as we go on. So I'm trying to formulate each statement in terms of minimal conditions, so to speak. So what is next? So there is a similar genericity result if you have lambda, the dissipation epsilon times rho, where rho is a constant, but you have to put the quantifier in a different way. So first you have to choose the Hamiltonian perturbation. Depending on the Hamiltonian perturbation, you have to choose rho, and depending on this, you have to choose epsilon. So under this condition, I want to, again, expand the scattering map as in terms of powers of epsilon, and it's going to be the same, the expansion looks the same, except that the vector field is no longer Hamiltonian beforehand. Okay? So the idea is to compute this vector field explicitly. So it's again Melnikov type of computation. So so this is a general formula for the change in the action for a general non-conservative perturbation. So it's order epsilon times you take the derivative of the directional derivative in the direction of the perturbation of the action coordinate along the homoclinic and subtract the effect on the matching orbit in the NIM. So when you apply this formula, so this was developed in a paper with, this is sort of classical Melnikov technique. So at least for us, the surprise is that when you put the dissipation has no effect. So the dissipation completely disappears. So the effect of the perturbation in terms of the action variable is the same as if you have only Hamiltonian perturbation. Of course, this is up to order epsilon square, but this is all we need. So the action is the slow variable. So the other, we have a similar computation for the change in angle by the scattering map. The angle is like the fast variable. So the computation is a little bit more involved, but it's at the end of the day, it's just a Melnikov type of computation done with a little bit of care. And so this is the general formula for a non-conservative vector field. And when you apply this formula for our specific perturbation, which is Hamiltonian plus dissipation, again, the dissipation term disappears. It vanishes, and the change in angle by the scattering map is exactly the same as if you had only the Hamiltonian perturbation up to order epsilon square. So this is very good news because so far we see that the dissipation has no effect in terms of the scattering map. So the dissipation is the same as in the case of the scattering map when the perturbation is Hamiltonian. And therefore,
but this doesn't include, here you don't use that rho is small.
Here I don't use the rho is small, yes. So I don't use, so this works for general dissipative perturbation of which acts on the action variables, on I and on P. So more abstractly, you need the perturbation to be conformally symplectic. So this is. So again, this is, it turns out that again, the first order term in the expansion of the scattering map, it's a Hamiltonian vector field, and this can be explicitly computed. So this is what people call the Melnikov potential. And there is a little bit of manipulation here to express the two components of this first order term of the scattering map in terms of the Melnikov potential. So I'm not going to go through all of these manipulations. And you reduce from the flow case in the extended space to Poincaré section and to a map. And you essentially have exactly the same result in the Hamiltonian case. So if you want to grow in the energy of the rotator in the action, you need that the I component of the first order approximation of the scattering map is positive. So if it's positive at one point, remember, so this is an order 1 computation, it's positive in a neighborhood. So you know that there is a trajectory along which the action of the rotator grows, and then essentially you want to follow that path. So I think I said at the beginning that we want to be very concrete, just to have an explicit example that goes from more or less A to Z. So I'm choosing now, so the results up to now, they are somewhat general, but now I choose a particular perturbation which is of this type. So this is the Hamiltonian perturbation. So the role of this factor cosine of q is that the perturbation vanishes at the hyperbolic fixed point of the pendulum. So you don't need to apply persistence of the normally hyperbolic invariant manifold. The normally hyperbolic invariant manifold persists from the unperturbed case. So this is a choice of convenience. This other term is like the first order truncation of Fourier expansion. And this makes our life easier because in this case you can actually compute this Melnikov potential. So the Melnikov potential is the one that we use to derive the scattering map. So if we choose this particular perturbation, then it turns out that the Melnikov potential has a explicit expression which is given here. It's in terms of hyperbolic trigonometric functions, and this computation was done explicitly in the scattering map was done in a paper by Amadeo Delchams and Rodrigo Schaeffer in 2017, where they explicitly computed the scattering map. So what you have here are the level sets of this reduced Melnikov potential. So the idea is that these are the curves that the scattering map will follow. So they are explicitly computed, and in one direction you go up, and if you sort of move around, then you go down. So you have you can choose always a region of order 1, which is filled up by curves that if you follow, you only move up. So again, what you have here in pink is a region in the phase space of the rotator where you have curves. These curves are the solution curves of the Hamiltonian that generates the scattering map. And if you would follow these curves, you always go up in the energy of the rotator. And you don't have just one curve, you have an order 1 family of curves. And this is kind of important because we need them all. So from our estimates on the scattering map in terms of the gain of action by the scattering map, each application of the scattering map goes up by order epsilon in the action. So now I'm just going to present the geometric idea of the proof without going much into the quantitative details. So this is the region where the scattering map takes you up, and this is filled up by good curves, the curves that moves you up. So and this is, in dark is the attractor, so the attractor tries to drag you towards it. So you use one step of the scattering map. So let's say you are above the attractor. If you are below the attractor, the attractor actually helps you. So you go towards the attractor, so this is good. So, but if you are above the attractor, you do one step of the scattering map, it goes up by order epsilon. But then you have to use the inner dynamics. So the idea is that because this is order 1, the domain where you have the scattering map giving you an increase in the action, this is order 1. So it takes you order 1 times to come back to this region. So if you use the inner dynamics, in order 1 times you are going to visit this good region over and over again. So you can actually do explicit estimates of, so whenever you use the inner dynamics, so if you are above, you are going to lose action because you are moving towards the attractor. And you can compute, you can estimate explicitly through Gronwall. Great, thank you. For instance, what is the maximum loss of action if you iterate the inner dynamics? Of course, at this point, you have to specifically say what is rho epsilon. So we use rho epsilon equal to be of the order epsilon over ln of 1 over epsilon, so it's fairly small. We are not sure if this is sharp, so maybe we can do better. So maybe this is the reason why I didn't put epsilon over ln of 1 over epsilon, because we hope to improve maybe. So I only put the less precise statement. If rho epsilon is sufficiently small, what you win by the scattering map and what you lose by the inner dynamics, at the end you win by the scattering map. So let's just say you gain epsilon, and you can choose this rho epsilon explicitly, and you have the return time explicitly estimated. Then you lose by the inner dynamics at most epsilon half. So then at the end of the day, you gain epsilon half. And you repeat this many, many times, and then you get diffusing orbits. Okay? So everything is more quantitative and more explicit in terms of what is rho epsilon and what is the estimate on the time than what I put on these slides. But I'll be happy to discuss about the details. And I think I am pretty much done ahead of time. So I mentioned the papers that this talk is based on. So this is with Derayave and Masser. And this is a paper with Akinbade and Teresara. And that's all. Thank you.
Questions?
Probably got distracted. I didn't understand what in the concrete example how it looks like the dissipative perturbation. So what is the form that you choose for the dissipative part of the perturbation?
For the you mean for the coefficient of the perturbation?
Rho epsilon I understand, but rho epsilon will be multiplied by something, right? So I didn't understand.
The dissipation is epsilon times rho epsilon. So this is the coefficient of dissipation. And
The vector field?
And the vector field acts in P, so you multiply negative epsilon, rho epsilon by P, and by you also multiply the I component, or I minus omega star. That's why it makes it conformally symplectic.
Yeah, that's what I wanted to know, exactly how you get this conformally symplectic.
Yes. Yes. So it's the simplest model for dissipation, right? It acts only on velocity.
So to see that the scattering map wins over the inner dynamics, you computed the time of the
Yes.
diffusion. And how is related with rho epsilon? I mean,
Yes. Very good question. So the time it's so essentially so I said, okay, let me go back to here. So the time to return to this region by the inner dynamics is order 1, but order 1 is not going to help you, because what you really do is move on the homoclinic until you get sufficiently close to the NIM. So if you want to get epsilon close to the NIM along the homoclinic, the time is ln of 1 over epsilon. So then the idea is that how did we choose the dissipation? We want time multiplied by the dissipation to give you epsilon times a constant. So that's why we chose this dissipation to be epsilon divided by ln of 1 over epsilon, because when you multiply by the time, you get a fraction. So the idea is that you win by the scattering map an epsilon, and you lose a fraction of that epsilon.
Then another question. You can consider also autonomous perturbation, right? Instead of the H1,
Yes.
time periodic.
Yes.
Would consider also autonomous, but maybe it's technically more.
Typically, it's the same, because you work in the extended phase space. If you wish, you add an extra variable and you make it autonomous. So there is no major obstacle to consider autonomous perturbation, as far as I can tell. We do not foresee any obstacles in terms of the dimension, because we use the scattering map. The computation for the scattering map goes in any dimension, and for the inner dynamics we use very basic tools to estimate the loss. So this attractor, it's, as I said, it's a gimmick. So. Sure.
Any other questions?
One comment about what you were saying. If it's autonomous, being symplectic is different than what you get, right? I mean, one thing is being symplectic at the energy level, so to speak.
Yes. Okay.
Than symplectic in the whole space. So I don't know.
Yes.
What would happen there?
Well, yes. So then the question is, how do you choose this dissipation? Which variables it acts? So. Yes, I think this is right. So you have to be more careful for it.
No more questions or comments? We can end a little bit ahead of time. So let's thank Riemann again.
Thank you.